All right, you guys, welcome to week 2 of chemistry. Today, what we're going to be talking about are molar ratios and molar mass. So let's go ahead and get started. Now, last week, what we talked about were how to balance reactions. And one thing that I want to bring to your guys' attention is that a balanced reaction can often be looked at as a recipe. So what I have on my screen right now is actually a recipe for some banana bread. So there's a couple different things that I want to point out when you're looking at the recipe. The first thing I want to point out is notice that you have a number, the amount. So for example, your 2 and your 2 cups of flour. So you have an amount. The second thing that you have is you have a measurement. So you're saying, how are you measuring that amount that you're talking about? And the third thing that you have is you have the substance that you're talking about. So when you're looking at, say, your 2 cups of flour, you know that you're talking about 2. You know that your measurement is cups, and you know that what you're measuring is flour. Those 3 things will become really important when we talk about chemical reactions. So as you can see, every single ingredient and every single thing on that recipe has those measurements. Now, if we take all of those ingredients and we combine them in that way, what you will see is that we will be able to create 1 loaf of banana bread. Now, the important thing that is brought up in this recipe is the idea that you are given ratios. You are given ratios of your different ingredients and how they combine with each other. So for example, when you're talking about the amount of flour in the recipe to the amount of butter in the recipe, it is a 2 to 1/2 ratio. For every 2 cups of flour, you need half a cup of butter. That's really important. You can't change one without changing the other. So if you wanted to double the recipe, you need to make sure that you double both the flour and the butter. Another example that we could look at is your eggs to bananas. So for every 2 eggs, you need to make sure that you have 2.5 ripe bananas in your recipe. So let's go ahead and let's see how this actually applies to a chemical reaction. So here what we have is we have a simple chemical reaction. We have some magnesium and oxygen reacting together to form a compound called magnesium oxide. Now, if we were to talk about the ingredients and we were to apply our 3 things, let's look at magnesium. We know we have 2, so that's your amount. You know that your measurement is moles. We talked about this last week when you're talking about reading a chemical reaction. You can only read a chemical reaction with the units of moles or molecules. When we talk about this in here, we're talking about mole to mole ratio, so we're going to be using moles. And the third thing that we have is we have what we're talking about. So we have the fact that we're talking about magnesium. So 2 moles are measurement of magnesium in our ingredient. So how would we say the next one? How would we talk about oxygen? Well, we know we have 1. There's that invisible 1 there. 2, and then our measurement is moles, and our substance is oxygen. So we have 1 mole of oxygen. And what do we produce? Well, we produce 2 moles of magnesium oxide. So notice, very much like a recipe, you're told the amount, you're told the measurement, and you're told what substance you're talking about, and then you're also told how much you're produced. So if we were to talk about ratios, let's look at the ratio of magnesium to oxygen. Magnesium and oxygen will always react in a 2 to 1 ratio. You will always have 2 moles of magnesium for every 1 mole of oxygen. If you were to talk about magnesium to magnesium oxide, sorry, my face is covering up part of that, it is a 2 to 2 ratio. So for every 2 moles of magnesium, we're always going to be producing 2 moles of magnesium oxide. If we were to double the amount of magnesium oxide if we wanted to double the amount of magnesium oxide that we produced, so say we wanted to produce 4 moles, we need to make sure that we double the amount of our reactants as well. So let's look at a quick example. So if we know the reaction and we know that they will always react in a certain ratio, so that 2 to 1 or that 2 to 2, we can use those ratios as conversion factors, and we can set up some dimensional analysis problems. So we're going to use that same reaction that we had on the previous slide, and we're going to look at this problem. How many moles of magnesium oxide will be produced if 4 moles of magnesium completely react? So notice that we're changing our ratio. So what we want to do is we want to start with what we're given. We know we have 4 moles. So let's go ahead and we're going to put that out in front. 4 moles of magnesium. Then we want to convert magnesium to magnesium oxide. So what we're going to do is we're going to figure out what is our mole to mole ratio of magnesium to magnesium oxide. Well, looking at a balanced chemical reaction and looking at those coefficients that are in front, we know that it is a 2 to 2. So notice that I put my 2 moles of magnesium on the bottom because I want my units to cancel out. And then I have my 2 moles of magnesium oxide on top. So if I were to go ahead and cancel those units out and then multiply across, what we see is that we would produce 4 moles of magnesium oxide. So notice how I can use those coefficients to convert from moles of magnesium to moles of magnesium oxide. So let's go ahead and I'm going to go ahead and switch the screens here in just a second. And what we're going to do is we're going to look at this example problem that we have. A little bit trickier than the problem that I had in the previous slide, but it'll be good practice for when you guys are doing your homework. All right, so here's the example problem that we're going to be looking at. So let's go ahead and take this piece by piece and let's look at the first part. So the first part says, what is the mole to mole ratio of carbon to iron? And you're going to have problems just like this in your homework. So we want to identify where carbon and iron are. Well, I have carbon right here and iron right here. Now, how do I tell what my mole to mole ratio is? Well, you want to be looking at your coefficients. So what does it say? It says that 3 in front says I have 3 moles of carbon to 4 moles of iron. So that is my mole to mole ratio. Again, just looking at those coefficients. So let's go ahead and look at the next one. What is my mole to mole ratio of the products? So what are our products? Well, our products are what are always found on the right side of the arrow. So our products now are iron and this CO2, which is carbon dioxide. So when we're trying to identify that, we're going to again use our mole to mole ratio. So it's 4 moles of iron to 3 moles of carbon dioxide. And they will always form in that ratio. So let's look at a problem that gets a little bit more tricky where we're going to have to plug in some math ideas. So how many moles of iron will be produced if 5.5 moles of iron, that's iron 3 oxide, were consumed? So we know we have 5.5 moles of Fe2O3, and we want to know the amount of moles of iron. So when you're thinking about this problem, what you want to think about is that you're going to be converting moles of Fe2O3 to moles of iron. So we need to figure out what our mole to mole ratio is of this. So if we look at our formula, we have 2 moles to 4 moles. So it is a 2 mole to a 4 mole ratio. Now notice that I'm not making this, or I'm not simplifying this ratio. You want to use the coefficients exactly how they appear in the chemical formula. So let's go ahead and set this up. When you set up the problem, you always want to make sure you start with what's given in the problem. And we were told that we have 5.5 moles of Fe2O3. And now I'm going to plug in my ratio. You want to make sure that you plug it in so that your units cancel out. And in particular, I want to make sure that my moles of Fe2O3 cancel out. So that's why I'm going to put that on the bottom, and then my 4 moles of iron on top. Now, you want to, when you're solving this and you plug this into your calculator, you want to make sure that you multiply the top and then you divide by what's on the bottom. So I'm going to take my 5.5, I'm going to multiply that by 4, and then I'm going to divide that by 2. And what I end up getting for that problem, oops, I'm on my wrong page, is that I get 11 moles of iron. So let's go ahead and do the same thing. A similar problem is going to be D. So how many moles of carbon are required to completely react with 6.7 moles of iron 3 oxide. So I'm going to go ahead and I'm going to switch colors so I can kind of point this out. So we have moles of iron oxide, and then we want to figure out how many moles of carbon. So again, setting up my problem, I'm given how many moles of Fe2O3 I have, iron 3 oxide, and I want to convert this to moles of carbon. So here we are, 2 to 3. That's my mole to mole ratio. I'm going to go ahead and move this up. So I have 2 moles of Fe2O3 to 3 moles of carbon. So this is going to be my ratio that I plug into my formula. So start off with what we're given. We know we have 7.65 moles of Fe2O3. Plug in my ratio again, making sure that this is on the bottom because you want it to cancel out. So my 2 moles on the bottom to cancel out, my 3 moles of carbon on top, units cancel out, multiply the top, divide by the bottom. So I'm going to take my 7.65, multiply it by 3, and then divide by 2. And I want the same number of digits that I have in my original. So I'm going to keep, and I'm going to have 11.5 moles of carbon. So if you were to look at this, my ratio is still the same as what it is over here if I were to set up my ratio the same. So let's go ahead and head back to the lesson and talk about molar mass. Let's go ahead and talk a little bit about molar mass. We have actually talked about molar mass before, and we talked about molar mass of individual elements. And when we talked about the molar mass of individual elements, we found those values on the periodic table, and they always had units of grams over moles. So for example, if I was talking about carbon and I wanted to know what the molar mass of carbon was, I look on my periodic table and I see that the molar mass of carbon is 12.011 grams per mole. So if I wanted to weigh out 1 mole of carbon, I would have to weigh out 12.011 grams of carbon. Okay. Now this is review. We've actually talked about this before, so hopefully this is just refreshing your memory. But what if I wanted to figure out, let me also back up. Sorry, one other thing. And remember, 1 mole of a substance is 6.02 times 10 to the 23rd particles or atoms. That's also important because that is the definition of a mole. And remember, we talked about the idea that a mole is this unit that we can use to count anything. If I have a mole of anything, I have 6.02 times 10 to the 23rd of those things. So if I had a mole of coffee cups, I would have 6.02 times 10 to the 23rd coffee cups. You could have a mole of anything and you would always have that amount. But what if I wanted to find the molar mass of a compound where it's not just an individual element? How do I figure out that molar mass? Well, it's actually pretty simple. So let's look at one quick example. What if I wanted to figure out the molar mass of NaCl, sodium chloride? Sodium chloride, as you guys probably know, is just our table salt, what we use when we're cooking and things like that. Well, what you need to look at is you need to figure out what is sodium chloride composed of. Sodium chloride is composed of 1 sodium and 1 chlorine. So all we need to do once we know what makes it up is we just need to look at our periodic table and we need to add up those individual parts together. So I'm going to take my 1 sodium and I'm going to add it to my 1 chlorine and I'm going to get the mass of my sodium chloride. So if you guys look at the bottom, sodium has a molar mass of 22.99 grams per mole. And I'm going to add that to the molar mass of 1 chlorine, which is 35.453 grams per mole. And that means that if I had 1 mole of sodium chloride, it would be 58.443 grams per mole. Now again, if I were to ask you, how much would 1 mole of sodium chloride weigh? Well, we know now, it's 58.443 grams. So let's go ahead and look at a couple different examples that might be a little bit trickier than the ones that we just looked at. So let's go ahead and switch the screens and solve those problems. All right, so we have a couple different example problems of compounds that we need to figure out the molar mass for. So let's go ahead and start with the first one. So our first example, our compound is MgO, which is magnesium oxide. So when you are doing these problems, the first thing you want to think about is what makes up this compound. Well, what makes up this compound is 1 magnesium and 1 oxygen. So when I'm calculating this, you should have your periodic table in front of you. And I need to say I'm going to multiply 1 times the molar mass of magnesium. And if you look at the molar mass of magnesium, it is 34.305 grams per mole. And you're going to do the same thing with oxygen. 1 times 15.999 grams per mole. So again, I looked at those values on my periodic table. Multiply those out and add them together, and you're going to get the molar mass for magnesium oxide, which is going to be 50.304 grams per mole. I'm going to go ahead and label this MgO. Now, just to kind of highlight an important idea, if I wanted to weigh out 1 mole of magnesium oxide, it would weigh 50.304 grams. So just kind of highlighting that key point. So let's go ahead and go on to the next one. Our next one is calcium chloride, CaCl2. So now we need to think about what makes up this compound. Well, we have 1 calcium, and over here, this 2 at the bottom tells me I have 2 chlorine, so 2Cl. So when I add these together, I'm going to take 1 times the molar mass of Ca, which is 40.078 grams per mole. And I'm going to say 2 times the molar mass of chlorine, which is 35.453 grams per mole. So notice I have to multiply that by 2 because I have 2 of them. All right, so add those together, and I get my molar mass to be 110.984 grams over moles of calcium chloride. So again, if I wanted to weigh out 1 mole of calcium chloride, it would have a mass of 110.984 grams. So notice that 1 mole of calcium chloride does not have the same mass as 1 mole of magnesium. All right, let's go ahead and scroll down a little bit and look at number 3. We have NH4, NO3. So this is ammonium nitrate. So let's go ahead and start adding up what we have. Well, I actually have nitrogen in 2 places. So I'm going to go ahead and combine those and say that I have 2 nitrogen. I have 4 hydrogen. And I have 3 oxygen. Whoops, there you go. So let's go ahead and add that together. So I'm going to have 2 times 14.007 grams per mole. My molar mass of hydrogen is going to be 4 times 1.008 grams per mole. And my molar mass of oxygen is going to be 3 times 15.999 grams per mole. So make sure you multiply each one of those by those individual numbers and then add them all together. And when we add those all together, we get 80.043 grams per mole. And that's ammonium nitrate. So I'm going to be redundant here. If I wanted to weigh out 1 mole of ammonium nitrate, I need to make sure that I weigh out 80.043 grams of ammonium nitrate. And again, notice that this molar mass is not the same as the other molar masses. All right, let's go ahead and take a look at our last one. Moving up, we have magnesium phosphates. So we have Mg3PO4 2. All right. We know our steps, so we're going to identify what we have. We have 3 magnesiums. Now, this 2 on the outside applies to everything in the bracket. So I'm going to multiply everything within those brackets by 2. So that means I have 2 phosphorus and 8 oxygen. So make sure that you distribute that 2 to everything within those brackets. So I have 3 times 24.305 grams per mole. I have 2 times 30.974 grams per mole. And I have 8 times 15.999 grams per mole. So again, make sure you multiply those out by how many you have. And when you add them all up, this one has a very heavy molar mass, 262.855 grams per mole. And that's of magnesium phosphate. So last time, I'm going to do this again. If I wanted to weigh out 1 mole of magnesium phosphate, it would have a molar mass. It would weigh 262.855 grams of magnesium phosphate. And as you can see, this one is the heaviest out of all of them. So even though they all consist of 1 mole, even though I'm talking about 6.02 times 10 to the 23rd molecules of each one of these, they all have different masses.